Okay, so the definition of the OR operator is a little bit different than the definition in English. If you go to a cafe and the waiter asks you, would you like tea or coffee, and you say, yes, both, that's probably not a useful answer, right? In English, when we say OR, we usually mean one or the other, but in logic and in mathematics, when we say OR, we mean one or the other or both. If you really do mean only one, then you should use the exclusive OR operator, which is different, so keep that in mind. So here's the truth table of the OR operator. So it's got two inputs, much like the AND operator. So I'll call the two inputs X and Y, and the output is going to be X or Y. So let's enumerate all the combinations, 0, 0, 0, 1, 1, 0, 1, 1, and let's draw out the truth table. Okay, so you can see that X or Y is true when at least one of the inputs is true. And the corresponding logic gate for the logical operator OR looks like this. Looks like a little spaceship thing with a curl on the back. So you can see the OR gate has got a curve on the back and the AND gate's got a straight line on the back. So don't mix these two up. Alright, the third gate we're going to talk about is the NOT operator. And the NOT operator basically takes the input and inverts it, or does the opposite, right? So if I say it's not true that I like bananas, that's the same as saying I hate bananas, right? It does the opposite. So it's only got one input X, and the output will be not X. If X is false, then not X is true, and if X is true, then not X is false. That's all it does. And the NOT gate looks like this. It's a little triangle with a little circle on the front. Whenever you see a circle on the front of a NOT gate, that basically means invert whatever signal is here, right? So if you put some signal in, the output will be the opposite. If you put an input high, the output is low. If you put an input low, the output is high. We use various different terminology for digital logic. We can sometimes use false or true, 0, 1, low, high. It's all the same thing. It doesn't really matter what you call the two states as long as you're consistent. So in this course, we usually stick to either true, false, or 1, 0. It doesn't matter. And the last operator is the exclusive OR operator. I pronounce it XOR. You might pronounce it XOR. Doesn't really matter. And the XOR operator is true when one and only one of the inputs is true. So let's draw the truth table for it. So we have X, Y, and X XOR Y. 0, 0, 0, 1, 1, 0, 1, 1. And here's the truth table. So it's true when one and only one of the inputs is true. And here's the logic gate for it. It looks like an OR gate, but it's got an extra line on the back. Okay? So those are the main operators you're likely to see in digital logic.